AutoChemplete is a tool to make structural formulas accessible to blind and low vision chemists. Auditive and tactile output solutions are not enough when documents themselves are not accessible. Note how the following is read aloud.
N, capital O, ho on O. Figure 1, chemical structure of caffeine.
With AutoComplete, annotators load in a structural formula. Then, based on an initial prediction, we show a series of autocomplete suggestions. The user can accept them directly or load them into the editor for further manual revision. As demonstrated before, the interface of AutoComplete consists of 4 core components. On the top left, we show the input image as extracted from the PDF document. Below that, we show the ML-predicted smile string based on that input image. To the right, we load this predicted smile string into the manual editor so the user, if they choose to, can make changes. The suggestions below, which can be directly accepted if a correct molecule is found, can also be refreshed if the user does make manual changes in the editor. To inform the design of AutoComplete, we conducted requirements interviews with 3 BLV chemists and 4 accessibility enablers to derive a total of 5 requirements. BLV chemists need exact labels to make up their mind on how a molecule is structured. Accessibility enablers caution us to be reasonably fast as they only have limited time available. Further, they need the tool to be skill supporting as they want to give this task to non-experts. BLV chemists use a variety of different output formats and modalities which need to be covered without redundant work. Lastly, the tool needs to integrate into existing processes and tools, covering steps like content segmentation and OCR. If we go through the process of annotating a document, we first take this inaccessible document and crop out the image of a chemical structural formula. We then use our system to predict an initial smile string. This smile string is being fed into a similarity search to produce a broad range of results. A human can then select the correct result from this similarity search. Based on this selection, we can generate various accessible representations. These could be visual, textual, auditory, or tactile, and in general produce an accessible document in the end. AutoComplete represents an end-to-end interactive labeling solution covering the accessibility of chemical structural formulas. To evaluate AutoComplete, we conducted think-aloud sessions with 15 participants with expertises ranging from chemistry professor to music student. We focused on student assistants at the Center for Accessibility at our university, as they were already accustomed to making literature accessible. Using thematic analysis, we derived a total of 7 themes. Initially, we can report success. E14 says, the tool is easy to use, there is a learning curve, for the first it took some time, and it just works after that. Furthermore, we find a common approach between experts and non-experts, where they compare images to find the correct molecule very quickly. We can gladly report that we cannot find motivational design trade-offs for competence support. For instance, from video game design, it's known that competence fostering, for instance the skill support that has been called for novices, should generally deplete autonomy for experts. However, as AutoComplete supports comparison formats used by both experts and novices, this is not the case. In this case, experts compare groups and substructures of these molecules, whereas novices compare them bond by bond and atom by atom. Participants all over the spectrum of expertise complain about something they called chaos in chemical structural formula annotation. They could easily, as E3 puts it, confuse a speck of dirt with a negative charge. The student assistants, who are accustomed to annotating math formulas with the LaTeX math mode notation, complain that they cannot really imagine how their blind peers would consume the content they have annotated for chemistry, as this will be converted into a different output format. Lastly, we can report success in that participants find AutoComplete entertaining, to work like a puzzle, or even would do this on a flight to keep distracted and for fun. To come back to our opening example, this inaccessible raster graphic of caffeine can be easily converted into a vector graphic that's better consumable by magnification, or into a tactilely accessible vector graphic for output on 2-dimensional braille displays. Furthermore, it can easily be read out like the following.
Caffeine C8H10N402, IUPAC1, 3, 7-trimethylpurine 2, 6-dione.